Don't go left rapids.
All right, so take a look at number 3. So number 3 says, a roller coaster descends from rest 35 meters from the initial drop. So this is going to be the initial drop. It's going to be 35 meters above the ground. So let's say something like that. And I've got a coaster train that is up there that starts off from rest. So its initial velocity is 0. So it doesn't have any kinetic energy. Does it have potential energy up there?
Yes.
It does. Okay, so it does have some form of energy. So its total mechanical energy is non-zero. And then it's going to go up the second hill. And it says the second hill has an altitude of 23 meters above the ground. So the question is, if a passenger at the top of the hill, so I'm going to draw the coaster train now here at the top of the hill. If the passenger at the top of the hill feels an apparent weight equal to 1/2 of her normal weight, what is the radius of curvature of that first hill, of this hill right here? Now, naively, one could say, well, shouldn't the radius just be half of 23? Is that a possibility? Well, does everybody agree that there are many ways that you can get up to an altitude of 23 meters? Let me explain. Would you agree with me that I could get up to 23 meters? This is the first drop. Would you agree with me that I could get up to 23 meters very quickly, very drastically? Does everybody agree? Another way to get up to 23 meters, and I need more space in order to do that. Can I erase this here? Okay. Here's another way that you can get up to 23 meters. Here's your initial drop. Does everybody agree that I could also get to 23 meters very, very slowly? Would you agree with me that the radius of curvature of that one would be much larger than 23? Whereas here, the radius of curvature would be actually much smaller than 23. Does everybody see that? So you can't just simply divide by 2. You can't do it. Okay, so what do we do instead? Well, we have to make use of the fact that the person feels half as heavy at the top of this hill. So let's see. Can we at least find out how fast this train is moving using energy? Can we do that? When it reaches that point. So let's call this point A, and let's call this point B. So let's try to do everything we know how to do using energy. That is a technique that I always recommend that you do. Suppose you see a problem where it's like, I don't think I've seen a problem like this before, but there's something similar that I do know how to attack using energy conservation. I know that I'm able to find out what the speed is here. So let's try to do that first and ignore the rest of the problem for the time being. And then I'll get to that at a later time. So let's see. So I'm going to use conservation of energy here. Here, gravity is the only force doing work because the track is frictionless, so we don't have any dissipative, non-conservative forces. So I'm going to use my equation for conservation of energy without any non-conservative forces there. So look at this. Do I have any potential energy when I'm here at this altitude? Yes. So this is going to be potential energy, which is going to be mg times the initial altitude, which is above the ground, which is 35 meters. Okay, so that's mgh. Does everybody agree that that's mgh? Now, plus, do I have any kinetic energy when the train is here? Do I have any kinetic energy? I do not, because I'm at rest. So does everybody agree that that term is 0? Okay. Now, potential energy when I'm at point B. Do I have any potential energy there? I do, because I'm elevated above the ground, right? And here I'm really assuming that the 0 for the potential energy is here, right? On the ground. So this is going to be mg times the altitude above the u equals 0 line at point D, which is 23 meters. Plus, and I have some speed at point B, which I'm going to call v sub b. So therefore I have some kinetic energy, so that's going to be 1/2 mvv squared. Now here's the conceptual question. How would I know that I actually have a non-zero speed at point B? How would you explain that conceptually? Even though I started off with it at rest, how is it that I have a non-zero speed at point B? overall, in going from A to B, did I lose elevation or did I gain elevation?
Lost.
I lost elevation. Therefore, my potential energy has dropped. Would you agree with me that I have less potential energy at B than I had at point A? So that is a lost form of energy. Does everybody agree that I lost potential energy? But that energy was not destroyed, because you can't create or destroy energy, and it was not dissipated into the environment, because there are no dissipative forces here, like friction, for example. There's no friction involved here. So therefore, the total energy must be conserved. So if U goes down, kinetic has to go up by the same amount in order to actually keep the sum of these two quantities fixed, because it's conserved, right? So here's the thing. If U goes down, K has to go up. Does everybody see that in this context? So K goes up, which means that I'm going to be traveling faster when I'm at point B than I was at point A. Okay, that's the idea. All right. So now that we've got that, first off, you see that M is common, so you can divide by M. It's a non-zero quantity, so I'm allowed to divide by it. And immediately you notice that VB, which is the speed of the train at point B, is actually the only variable in that equation. Does everybody see that? So I could now solve for it. So I'm going to subtract, so I have G times 35 minus 23 is equal to 1/2 times the speed at point B squared. And I'm going to go ahead and multiply both sides by 2. So I have 2 times 9.8 times 35 minus 23 is equal to VB squared. And what would be the last step? Square rooting. So I'm going to find out what VB is. The speed of the train when it reaches point B. So let's take a look. So that's going to be square root of, and notice that the altitude difference is what plays the role. Does everybody see that the altitude difference is what really matters? Not actually how I got from point A to point B. Remember, gravity is a conservative force, therefore the path that you take, the work done by gravity is independent of the path you take. So all that it really cares about is the altitude difference. All right, so take a look. 35 minus 23 multiplied by 9.8 multiplied by 2, and then we're going to take the square root of that thing. So the speed of the train when it reaches point B is 15.37. And what are the units? Sorry,
Meters.
3-4. Meters per second. Excellent. So there it is, 15.34 meters per second. Now, that's still not telling us what the radius of curvature is for this part of the track. Does everybody agree that the radius of curvature would be from the center of curvature, from the instantaneous center, is what we call it technically, to where the train is at that moment? So we're going to call that R. So from the instantaneous center, that's the center of curvature of that piece of track at that moment in time. We want to know what that radius is. Now, what is that reminding you of? Radius, we're changing direction, centripetal. So we're going to have to go back to some concepts that we discussed in Chapter 6. So first off, let me draw a picture of the passenger inside of that coaster train. Here's the passenger as a stick figure of the passenger there. And what are the forces acting on that passenger right now? So is gravity acting on the passenger? Yes, because the person has mass, therefore it interacts with Earth's gravitational field. So there's going to be an interaction with Earth's gravitational field. So there's an mg force, right? But the person is also sitting on a seat, right? And gravity is pulling me down. What's preventing me from going through the ground right now? A normal force. Everybody agree that it's the normal force that the ground pushes back up on me. So if I sit in this chair, what's now providing the normal force on me? It's the chair itself. So everybody see that the chair is providing some normal force. Same thing's going to happen here. The chair is going to push, or the seat is going to push up on the passenger. So that's not a free body diagram because I have not actually isolated the body, which is the person inside of the seat, and represented them with a point. So I'm going to go ahead and do that. There's the person inside of the seat. There's the normal force. And there's the mg. Question for you, which one should be larger and why? Is the person accelerating when they're at the top of that hill? Remember that there are many ways that you can accelerate. You can speed up, slow down, or change direction. So are they changing direction when they get to the top?
Yes.
Are they? They are. They're changing direction, right? So there's an acceleration towards the center, which we call what? Centripetal acceleration. Notice that I've put a negative sign there. Why did I put a negative sign for the centripetal acceleration? Pointing towards the center, which means that that's below, that's pointing down, right? So that centripetal acceleration is down. So now, answer the question here. Which one is larger, the Fn or the mg? Mg, why? Because we are accelerating down, okay, towards the center at that moment in time, due to a change in direction. So here's the thing. Also, why are we drawing the free body diagram for the person and not the train itself?
Because we've been given the apparent weight of the person.
Very good, excellent. Because we've been giving the apparent weight of the person, not the train. So we want to draw the free body diagram for the person. Okay. All right, so now what I'm going to do is I'm going to sum forces in the y direction. Why in the y direction? Because all of the forces acting on this passenger right now are acting in the y direction, right? So I'm going to go ahead and sum. So let's continue this over here. So I'm summing forces in the y direction, and that's going to be mass times acceleration in y. So I'm going to have Fn, looking at my free body diagram over there, Fn plus negative mg is equal to mass times negative centripetal acceleration. Why was the centripetal acceleration negative?
Down.
Because it's pointing down. Excellent. At that moment. Now, do I have an expression or an equation for centripetal acceleration?
Yes.
What is it?
V squared over r.
V squared over r. Excellent. So right here, I'm going to put V squared over r. Hey, wait a second. V? Isn't that what we just used energy to calculate? Yes. Does everybody see that we had to use energy in order to find out what the speed was before we could even do this equation? Okay, so that's how they come together. So Fn minus mg, minus because it's a plus and negative, so that's a negative, equals negative mass times v squared over r. And this, by the way, it's important that you note, is actually the speed at point B, because we're trying to find out what the radius of curvature for the track is at that moment in time, when the train is at point B. Now, here's where the terminology comes into play. This is where you have to remember some of the terminology that we mentioned back in the forces chapter. It says that the person's apparent weight is half of their true weight. Now you have to remember that mg, this is called the true weight, right, of the passenger. And Fn, this is called the apparent weight. Okay, or is synonymous with apparent weight. So if it says that the apparent weight of the person is half of their true weight, does everybody agree that they're telling you in words that Fn is equal to 1/2 mg? Does everybody agree? So what I'm going to do is I'm going to substitute this guy in here. And why should the person feel lighter at the top of the hill? You actually answered that question when I asked you which one was larger, Fn or mg. Which one is it that they actually feel and is therefore called the apparent weight? Which one is actually sensed by the person? The Fn. So you're telling me here that Fn is smaller than your true weight, therefore you feel lighter than you usually do. Okay. So here's the thing. What we're going to do is we're going to go ahead and put that half of a 0.5 mg in for the normal force. 0.5 mg is the same thing as half mg. So 0.5 mg minus mg is equal to negative m speed at point B squared over r. And look, there's the variable we're looking for. We're looking for the radius of curvature at that moment in time when the train is at point B. So first off, does everybody agree that I have an mg in common? Does everybody agree? On the left. What can I do if I have a factor in common like that? I can factor it, right? So I can say mg times 0.5 minus 1 is equal to negative mvb squared over the radius. Now, 0.5 minus 1, that's negative 0.5, right? So we're going to have negative mg times 0.5 is equal to negative mvb squared over the radius. Now, first off, what happens to the negative signs?
Cancel.
They cancel. Very good. And one more thing cancels. Since m is a non-zero quantity, may I divide by it? Mm-hmm. Yeah. So when I divide by it, the masses cancel. So now I'm left with G, which is just 9.8, times 0.5, is equal to VB squared divided by the radius. But wait a second, don't I already know what the speed of the train is when it's at point B? I do, that's what I used energy for. Let me go ahead and trip the sensor here real quick. Okay, so let's take a look. So what we're going to do, we're going to go ahead and take that VB, and we're going to substitute it in right here. So we have 9.8 times 0.5 is equal to 15.34 squared divided by the radius. So once I solve this algebraically, I end up with the radius being 48 meters. Which you notice is definitely not 1/2 of 23. Definitely not 1/2. Okay, so does everybody see how we got that? Can I clarify any of the steps? So, quick conceptual question. Which case was it more like? This, or was it more like this? Which one do you think? The second one. Very good. Excellent. Because look at this. They told me this height was 23 meters, right? This height's also 23 meters. But does everybody agree that this is saying that the radius is larger than basically the height of the hill? So that would mean that it would be something like this. Does everybody see that? As opposed to here, where the radius of curvature is actually less than the height of the hill. So actually it's more like this than it is like the first one. Yes, go ahead.
I just want to make sure I'm thinking about this right. So, like, for the person in the cart going over the hill,
Yep.
so if, like, the seatbelt or, like, the roof or whatever it has that's keeping it from, like, if that wasn't there, technically the person would just, like, keep falling out if there was nothing else, like, holding it down.
You mean if it
Or-
wasn't for like a shoulder harness or something?
Yeah.
Not really. Not really, unless it traveled too fast around the
Okay.
hill. So if it traveled too fast, there was a problem that I believe we actually did in class where, or maybe it was extra credit, where I asked you if I gave you the radius of this hill, or of a bump. Let's say it was like 3 meters or something, the radius of a bump. And I said, what was the maximum speed? Because obviously the car itself is not, it's in contact with the road, but it's not attached to the road. So it could fly off, right? So I asked you, what was the maximum speed that that car could have so that it does not lose contact with the bump and fly off and hit the road at some, later time. So yeah, so it still can maintain contact with the road even if it's not attached to it. So it's the same thing here, even if you're not constrained by a shoulder harness mechanism, you could still actually stay in your seat as long as the speed is below some threshold value. Yeah. Okay, so does everybody see how we got it? Is everybody comfortable? Yes.
So what are we saying with the radius of 48 meters?
We're saying that it's more like this case than it is like this case. Because here, the radius would be, if you notice here, the radius would be smaller than the altitude. So that would be like less than 23. The radius would end up being less than 23. But here, notice that the radius of curvature is much larger than the altitude itself. So, and that's what we expect because the radius ended up being larger than the altitude. Yeah. So it looks more like that than it does like that.
If it were like that first graph, they would feel even less than half the way, correct?
Very good observation. Yeah. So if it was like this, they would feel much less than half of the way. They would feel much more weightless. Like in a situation like this, if they weren't strapped in, they would probably fly out. Yeah. So it's going to depend on that radius. Okay, so let's take a look at the